So again, as I said, I'm Dominic DeCenio. I'm working with Megan Anderson to present to you demonstration days, software demonstration days. This week's installment is MHKiT. So I'd like to invite Swara, if you're on the call, to come on and give us a few words about the series.
Yeah, thank you so much, Dominic. Thank you, everyone, for making it to another one of Software Demo Days. If you've attended others, you know this is a set of online conferences we're doing to promote cross-collaboration and understanding of the various different marine energy software that we fund here at WPTO, but also other related software like marine energy software that we may not necessarily fund directly, such as what we're going to discuss today, MHKiT, presented by, I think I mixed up something differently. Sorry. But anyway, yeah, MHKiT, which is created by Andrew Sims at NREL, Rebecca Fow, and Adam Keister. Rebecca's at NREL and Adam's at Sandia. So with MHKiT, which is a software that we fund, so it's an open software marine renewable energy software developed in Python and MATLAB that includes modules for ingesting, quality controlling, processing, visualizing, and managing data. And basically, it entails quality control for data cleaning, resource assessment, loading graphics, and other related functions, and is overall able to identify extreme conditions and the forcing on devices. So overall, it's a very useful tool that I'm looking forward to hearing Andrew and the team discuss more on today.
Thanks so much. So you can turn it over to the MHKiT team, and I'll just be jumping on later to show you how to get into CoCalc and use your environment. But the rest is up to them. So thank you so much for joining us, MHKiT, and please introduce yourself and take it away.
Thanks, Warren, Dominic. I'm Adam Keister. I'm at Sandia. I'm one of the MHKiT developers.
Andrew Sims, data scientist at NREL, also one of the MHKiT developers.
And I'm James McVeigh. I'm at PNNL. And yes, I've been on the MHKiT team for quite some time. And I think, Adam, you're going to get us started with this presentation, and then we'll jump into examples.
Will do. Okay, thanks everyone for joining. I know we have a couple other MHKiT team members on the call, but Andrew, James, and myself will be presenting about MHKiT today. MHKiT is the Marine and Hydrokinetic Toolkit. It is a free and open source software for processing, analyzing, visualizing marine energy data. So compared to some of the other demos we've seen in this series, MHKiT is not a simulation tool, it is a data processing tool. So we have two versions which are nearly at parity. They're in Python and MATLAB. Like a lot of open source software, we're actively developed on GitHub, and we're supported by 3 national labs, Sandia, NREL, and PNNL. MHKiT covers a wide breadth of marine energy. So there's functions within MHKiT to do resource characterization that focus on wave or current data, or field measurements, lab measurements, or simulation data as well. And really one of the main goals behind MHKiT is to implement the various marine energy standards within IEC 62600. You can see some of those that are relevant to MHKiT here. We also follow the 61000-4-7 with regards to, I think, electrical power quality. So we really want to emphasize that MHKiT is a tool you can all use to take a wide variety of marine energy data, use MHKiT to analyze and process it, and when you're done, you come out with an IEC standards-based analysis. I'll go into some of these modules in more detail, but at a high level, there's various modules within MHKiT for ingesting data. You can pull data sets or data from data sets such as NDBC, CDIP, NOAA, USGS, and the Wave hindcast. MHKiT imports PECOS to perform quality control and data cleaning on time series data, and then there's a variety of resource assessment modules, device performance assessment modules, and as well as modules for looking at extreme loading, power quality, and passive acoustics. And built into all these are various visualization capabilities. I'll go into these in more detail.
Are you in?
I'm just getting in. I couldn't find the link.
I clicked on the. Can you send me the link in the email? But
Okay, thanks. And so kind of why we want to encourage people to use MHKiT. Again, we really focus on implementing these standards in a way that is verified and documented. In addition to those, we do have functionality that goes beyond the standards and incorporates other tools. So for example, a couple of the tools that have come into MHKiT over the last few years are the WEC Design Response Toolbox and Dolphin, which we'll talk about. We also have a focus in MHKiT on developing examples using MHKiT and Python and MATLAB to give our users a head start with their data processing and highlight how one can use MHKiT. It's been used for a long time throughout the marine energy community for several years. We really push, using a certain format with MHKiT within using Pandas or X-Ray to allow people to bring in data and combine them into a common format. And we are still supporting MHKiT, so we're continuing to develop it and maintain and support it so that it's a reliable tool for the marine energy community. So I'm going to go into the various MHKiT modules in more detail now. We have quite a few here, some of which I think I highlighted already. There's a variety of modules focused on different energy types, wave, river, tidal, Dolphin to read ADCP and ADV files. We also have loads, mooring, power, and passive acoustics. So I'll go into each of these in some more depth. So starting with quality control in MHKiT, we're really pulling in PECOS, which is another Python tool which was developed specifically for the quality control of time series data. And so we import this into MHKiT because it's a very important step whenever you're pulling in any kind of numerical data and analyzing it. You need to process it and clean it up beforehand. We try to enable users to do that by pulling in PECOS. For example, you could fix missing data, corrupt data, remove outliers, look at where you're might be missing data. For example, here you can see, if this was a device measuring some quantity, there's some kind of issue here where they didn't have data. So this is a very important step to do before going and analyzing anything else. The wave module within MHKiT is geared towards characterizing wave resource and characterizing WEC performance. So within the wave module, there's a set of I/O functions that can pull in WEXIM or SWAN model results, download data from the wave hindcast or from CDIP and NDBC. And once you've done that, you could go, for example, if you're pulling in the hindcast, CDIP or NDBC data, you could assess the resource you're getting from those data sets and calculate metrics like significant wave height, peak period, energy period, the spectra. If you're pulling in model data, you could also quantify the performance and you could use MHKiT to create capture-like matrices or calculate mean annual energy production. And then we have a graphics module within Wave that will visualize many of these quantities. The river and tidal modules are set up in a similar way. In this case, the river module's I/O is focused on downloading and ingesting USGS river discharge data. And then the river resource module allows you to calculate the, for example, exceedance probability or your inflow velocity at a given site, or calculate power. There's a few performance metrics as well. You can calculate the equivalent diameter or capture area of a turbine. Now in this river module, we're starting to look at the IEC-301 and -300. And similarly, there's graphics capabilities to plot a lot of these metrics that are calculated in MHKiT. The tidal and river modules overlap quite a bit, but in this case, the tidal module is ingesting NOAA tidal data. You could additionally calculate and visualize the principal directions of your flow and look at the difference between ebbing and flooding of tidal currents. Dolphin is a widely used module within MHKiT. It's a very complex one. It was developed several years ago. It has now been brought into and is maintained in MHKiT. And Dolphin is a library to read and process ADCP and ADV data, specifically NORTEC and RDI devices. You can also use Dolphin and MHKiT to change between various coordinate systems, analyze your turbulence statistics, and other quantities of interest. The loads module within MHKiT is focused on assessing mechanical loads. So for example, you could calculate blade moments and look at statistics of, for example, a bending moment on a turbine blade in this plot here. You could also use the loads module to look at extreme loading cases and visualize those various quantities. The mooring module is a new one within MHKiT. Right now, the mooring module will import data from Moordyne, allow you to calculate the lay length of a mooring line and then visualize it in 2D or in 3D. This is a fairly new module within MHKiT, and like all of them, we're always interested to hear if other people have, in this case, for example, data analysis code relevant to mooring lines that would be valuable. We'd be interested to bring that in and support it in MHKiT. The power module is focused on electrical power quality. So there's functions in here to look at the harmonics of electrical power, interharmonics, then also calculate the total harmonic current distortion. Again, visualizing those quantities that are calculated in MHKiT power. The passive acoustics module is also a new one. This module brings in some work from Joe Haxel at PNNL and gives the capability to read .wav files from hydrophones, clean up the audio time series, and then convert and look at your spectra, sound statistics, and then plot, for example, the spectral densities or spectrograms of a hydrophone. Any questions on various capabilities in MHKiT? There's a lot in here, and like I said, there's quite a wide breadth of functions in MHKiT. So I'll keep going on. For all of these modules, we have plenty of examples available. So before we actually jump into walking through some demos, I want to point out where those are. So if you went to our documentation page and looked at the examples, you can see these long tables of different examples we have in either Python or MATLAB and kind of what their topic is. So we also categorize each of these by whether they're related to wave, current, or resource, and whether there's an associated IEC standard. So I'd encourage anyone interested in MHKit to go get our documentation and follow some of the examples of how we recommend using MHKit to get a head start. So we're going to walk through 4 different examples today in both Python using CoCalc and then in MATLAB. So we tried to pick a variety of cases that'd be of interest to the group. So in Python, we're going to walk through a PackWave resource characterization, and then an example of reading ADCP data using Dolphin. And then we'll switch over to MATLAB and screen share, and we'll share how one could use MHKit and MATLAB to download the data from the WPTO wave hindcast, analyze it, and then also walk through a wave energy converter power performance example. So I think I'll turn it back over to Dominic quick, and we will get into CoCalc.
Yeah, thank you. So I'm just going to take you through kind of going, getting into your project so you can start up using the notebooks that we've set up for you. So I'm just going to throw the link in the chat. You should just go to CoCalc. I'm going to share my screen too so you can see what's going on. So if you just go to CoCalc-projects, you'll have to log in to your account. And you should see available projects here in these cells. Yours will look slightly different than mine because I'm a collaborator. So yours will look like this. It'll have your name and then a hyphen and then WPTO software demo days. So just first navigate to the link, log in, and then come to this project. And then within the project, you got all the different demo days software. So you'll just navigate to the MHKiT folder. So once you're there, you have all the resources for the demonstration. So there you go. And I'll stop sharing and then let them take it away.
Okay, thanks, Dominic. So I'll go ahead and share CoCalc. And so I'm opening up CoCalc and going into MHKiT now. So I invite everyone to follow along as we walk through these couple examples. So we're going to start with the PackWave resource characterization. And all of these examples are also available on our GitHub page with the associated data. So for example, we just uploaded the ADCP example, PackWave, and then one extra just in case. And if you looked in data, for example, you'll go in and we can see some Dolphin data that we'll go in and read later. But I'm going to back out, go back to MHKiT and open up the PackWave resource characterization example. So as everyone gets started, I think the first thing to check here is to make sure we're in the MHKiT environment, which it looks like it's probably already selected, but if not, I would double check this upper left-hand corner to see MHKiT. And if it's not selected, I think you can go down to kernel and select the correct Python kernel, which is the MHKiT environment. So to start, ignore that. I'm going to start just by running all of the cells in the notebook. So as we go along, the different cells we walk through will be completed. So this example is following paper Dunkel 2020, which is characterizing the wave resource at the PackWave site following the -101. So we're gonna mirror some of the things they did in that paper and use MHKiT to analyze the resource here. So the first step is just importing all of the Python dependencies we'll need for this analysis. So we'll import MHKiT and a variety of other Python packages for plotting, and then kind of our general science and engineering packages like SciPy, Pandas, and NumPy. There's one thing that is taken out of this example, which I'll switch over and show you quick. But so if we're analyzing the resource at PackWave, we want to make sure we're selecting the NDBC buoy that is most appropriate. So if you looked at our original example, there's one other thing that we had to take out on CoCalc. For example, here we're just plotting the two different PackWave sites and then the closest available NDBC data. Sorry, NDBC buoy. So we have PackWave South, PackWave North, and then this buoy number 46050. So once we know the buoy that we want to use, we're going to go into MHKiT and start getting some information about that buoy. So this is a submodule within MHKiT, and we're going to use our buoy number, again, 46050, to first look at some metadata for that. So we can use MHKiT to pull this metadata from NDBC, and we're printing out, we can see the name of the buoy, who's maintaining it, the type of buoy it is, its location, and then some various information about the elevation of certain measurements. So moving on, once we have decided this is the right buoy we want to use to characterize this site, then we can use the MHKiT available data and request data functions to actually download that data locally so we can use it. So first thing we're going to do is specify the parameter we want to use. In this case, we want to look at the spectral wave density. The NDBC parameter is Sweden. That's how I pronounce it in my head. And so we can get all the available data for spectral wave density from this buoy using available data. And then once we do that, we can actually request all of that data. And so we pull all of the files that are associated with that variable in that buoy, and then we download them locally with request data. And this is going to print out a subset of the 2020 data. So looking here, we can see we have, this is hourly data for 2020, and then the spectral wave density. This would be the frequency dimension. And so we have frequency and then time. The first things we're going to do to make that data a little more useful is to actually create a time index from that separate day, month, year, hour, and minute. And so we use a function with MHKiT to loop through every year, and we create a more useful time index for that information. Yeah, it's the same data now, but it's in a little more useful format. And now this example is going to walk through calculating a variety of quantities of interest given all of this wave spectral information in 2020. And so here we're going to pull a variety of functions in MHKiT to calculate the significant wave height, the energy period, and the energy flux, as well as the peak period and the zero crossing period. And so this cell is looping through every year in the data that we downloaded. It's creating lists of these different quantities, and then creating more convenient pandas data frames of this information. And in this case, we're looking at energy period, peak period, significant wave height, the energy flux, and the zero crossing period. And the last thing, we could also calculate the wave steepness. Okay, so I'm going to keep moving along. So now that we have all of the wave statistical information about this site, we're going to go down and look at the annual energy matrix. So, oh, I should start. Actually, I skipped. There is some cleaning. Again, I emphasize cleaning at the beginning. So this is a simple step to remove outliers in energy flux and significant wave height. So once we've cleaned our data, we'll go through and create this wave matrix of the site, and we can see what wave conditions at this site have the most energy, and then how frequently you see those wave conditions. So you see most of our energy at this site is concentrated in this range of, this is roughly like 9 to 11 seconds, and a wave height of roughly like 2 to 4 meters. We could also use MHKiT to look at the power by month. So this plot we're going to show, it's getting a little large to screen share. In this case, we're showing for each calendar year our various wave statistics. We could look at how wave height or energy period change during the year. And I think unsurprisingly for this site, we're seeing larger significant wave heights in the winter months and smaller ones in the summer months. There's different ways we could represent that same monthly data. We could look at the cumulative distribution of energy flux for each month. Again, calling a function with the MHKiT graphics. This will be MHKiT wave.graphics. And then I'm going to skip down a little bit. So the other thing we can do using functions within MHKiT, which are coming from the WAC design response toolbox, is look at the extreme sea states. So we can create some environmental contours using this information and look at our extreme wave conditions for the 50-year or 100-year conditions, given the hourly data from this buoy. I forget off the top of my head how many years we're pulling at the beginning. I have to go check on how many years are going into this calculation. There's also some functions with the MHKiT where we could represent this sea state using some clustering methods, which allow us to greatly down select the amount of data we have here and select those sea states that are most representative of the site. We can iterate through the number of clusters we want to create to represent the site and look at where our total energy is most accurate. So this example is looking at creating 4, 8, 16, or 32 clusters to represent all of these hourly wave conditions that we pulled from NDBC. I think the last thing this notebook does is it takes those clusters and it's going to compare the total energy flux for those clusters to the total that come from the measured NDBC data to look at what's most accurate. So in this case, we see as we get up to about, say, 32 clusters, we're very close to the total energy that's seen at the site from NDBC. So yeah, I think this is a great notebook to reference, and I encourage anyone who wants to use MHKiT to look at wave resource to go reference this, and it'll walk you through, again, all the different ways you can do that and point you to those functions in MHKiT that allow you to do a resource assessment like this. So I think we're gonna switch over to James now and look at the ADCP example in CoCalc.
Sounds good. Shall I steal the screen?
Yep.
Since I had not had a chance to learn how to switch to dark mode, we're going to go back to light mode. Alrighty, so I'm going to be walking through a notebook that describes how to process a very particular instrument called an ADCP in MHKiT. This is a notebook I've shared with, I think, a couple of you on the call who are also new to these instruments. To start, an ADCP, first of all, is basically the underwater equivalent of a LiDAR. So LiDAR uses light beams essentially to measure wind to ranges of kilometers above either the surface of the Earth, or you can have it pointed out from the nacelle of a wind turbine, which is also quite common. ADCP is the acoustic analog of that. So we're using sound to measure velocity underwater as opposed to using light to measure velocity in air. As such, you get all of the stipulations and complexities that come with using acoustics in an instrument. And so what we're trying to do with MHKiT and this notebook is simplify that process, or at least walk you through how to do so. And so in this notebook, we show how to import data. We do some reviewing, quality control, some data averaging, which is important in general for these high sampling rate instruments. And finally, at the very end, this goes through how to calculate turbulence stats with a 5-beam ADCP. That really, I'll just cover turbulence intensity. The rest of those parameters, if you're interested in validating models, is what you're going to look at. But I'll just walk through, essentially, I'm just going to walk through the velocity measurements and some basics that I think most people who are using ADCPs are interested in learning. To start, I think I'm just going to reboot my entire kernel. And then I'm going to go ahead and get this started because this took a solid minute to import when I started this. I think last point of note on ADCPs, the data you're getting out of these guys is multidimensional. They're taking a profile across the water column. So you have a dimension in time, you have a dimension in space, which is a single dimension, and then you have the multiple beams in order to get a vector, say in an instrument XY Z coordinate system or an east-north up, which is the most useful. So with that very quick background, I'm going to dive into it. So I went ahead and ran this first function block to import the module itself. The next function block here is reading one of these raw binary files that are coming directly off the instrument. We support Nortec and Teledyne RDI ADCPs. If you have Sontec instruments, I'm sorry, we do not know how to read the Sontec binary files, though they're less common nowadays. So this is a file you're going to get straight off the instrument. With Nortec, it's .82CP. RDI has various, but I think they're consolidating around the .pd0 data file. So honestly, this read function is the main bulk of the package. If you have an ADCP and you read the file and you get an error, please throw up a issue on our GitHub page. This package has essentially been built by getting a lot of different instrument files, running a lot of different configurations, and then fixing all of the bugs. So with that out of the way, we have read in the data set. We're gonna print the data set to show you what that looks like. So we're using a file format called netcdf. Netcdf is a multi-dimensional file format that is very useful for storing most types of environmental data. If you're familiar with meteorology and forecasting, this is often used to store raster layers and geographic layers in a single format. That's relatively easy to use. In Python, we're using a package called xarray. Xarray you can think of as a multi-dimensional version of pandas. If you don't know what pandas is a two-dimensional. Pandas is very good at reading 1- and 2-dimensional data and storing additional metadata with it. And what I mean by metadata is the nice thing about Jupyter Notebooks is that they have a very nice UI, user interface, for looking at netcdf files in Xarray. What I mean about metadata is that you can store, say with our variable temperature, you can store units and other information along with the data itself. So in Jupyter's UI, you can hit this, I'm not even sure how to describe this cylinder, to look at the data itself, and then the script button to look at the metadata. But the main variable we're interested in, or most people are interested in with ADCPs, is the velocity, shorthand VEL here. This is that multi-dimensional time series that I mentioned before, where the first dimension is your direction. So that's your vector direction, X, Y, Z, east, north, up. Range is your profile in space, and then time is, of course, time. And so there are a bunch of other variables in this data set. Essentially with Dolphin, we try to give you everything that is stored in that raw binary file, which is probably more than you ever wanted. And the last thing to know about is that we can also store global attributes in a data file. So this is not scrolling for me very well. So this contains a bunch of information that's also stored in that binary file that is useful for the processing of the rest of this information. I do not know what I just did there. I did a bigger full screen already. Click, Shift, Enter. There we go. A secondary view. If you want a more simplified version of this, you can use this .belds shorthand, and it'll give you a very quick pinout of how much data you have, what reference frame it is, how many pings, that's an individual profile you're taking at what sampling rate, and then a bunch of variables. So with that out of the way, hopefully you're now all experts in X-ray net CDF and ADCP, reading ADCP files. So as Adam mentioned, the first thing we'll dive into is quality control. The first thing before quality control we'll do with ADCPs is actually setting that range coordinate. So that profile it's taking 0 is starting from the transducers itself. And generally when you're deploying an ADCP, it's either you're deploying it on top of a tripod off the bottom, so it'll have some set difference from the seafloor that the instrument's sitting at, or it will be deployed some distance beneath the vessel. If you have it deployed horizontally, you might be able to skip this part, but horizontal deployments are somewhat rare. So to set the deployment out, first we actually want to look at, we can plot the velocity to actually show you what we're looking at. So we have time on the x-axis, the profile on the y-axis, and then a color bar. This is, X-ray has some internal plotting tools that I believe I use for most of this notebook. It's just a shorthand, quick and dirty way of showing what we're looking at. But when you first look at the data, you're going to have 0 is going to be from the transducer. The range is going to be whatever your max profile setting is, and then you're going to have a lot of velocity data in here. So with this first step, what we're doing, and I'll explain more of what's going on in this data itself later. First thing we're doing is setting the 0 point to actually be the seafloor. And so we have a specific function to do that. In this case, the lander is about 0.6 meters tall. And so I'm setting the ADCP itself to start at that distance. It will add 0.6 meters to the initial part of this range, which was also 0.6 meters. If you're curious why that is, I believe I explained that up here. But in the interest of time, I will keep going. With all that said and done, that means our first data point measurement is at 1.2 meters above the bottom. So this first, you can't see it here, but they're essentially, you can kind of see little bars that come across. The center of this lower depth bin, as it's called, is at 1.2 meters. And in case you forget, that is in the description here. So once you have that profile set, we'll do some first quality control is that we actually need to figure out where the water surface is. So we have a couple functions. There are several functions in Dolphin to do this. One, if it's a ADCP sitting on the bottom looking towards the surface. We have some functions to just look at the pressure sensor on the ADCP to figure out where the surface is. If it's a down-looking ADCP looking towards the seafloor, and that ADCP doesn't have a depth sounder of some such on it, there is another function to try to look at some acoustic backscatter to figure out where the seafloor is. It's not quite as good, but it does exist and it's a good first pass. So if we run these two functions, what we're doing in this first function is we're saving a variable called depth, I believe, in place. And then with the second function, we're looking at that variable depth and deleting all that from the data set. So we plot our velocity again, we'll see that a decent chunk of our profiles have been removed. That's everything above the surface and a little bit below the surface. If you look in our original plot above, you can see the surface is this kind of lighter bar in between here. Everything above this bar is actually a reflection of the sound signal back in the water column. So we'll get rid of that. We'll do some basic quality control. There are some ADCP specific quality control. Some ADCPs have a long beam measurement that's called an acoustic signal correlation. This correlation is essentially a measure of what the ADCP thinks is a good or bad quality measurement. If you plot that, you'll get something like the following. In this instrument, it's in units of a percent, where 100% is great and 0% is bad, as the ADCV thinks. What is good or bad is somewhat relative. You may have to do some digging to actually, or some experimentation to actually figure out what of those bins is bad, if any. A low correlation may not be bad. There just may be low signal reflectivity in the water. But you can dive into the weeds with that. But what I'll do here, I'll just set the correlation filter at 50%, which is with this quite simple .clean as a submodule correlation filter. Set it to 50. That'll automatically remove all those correlation data points that are less than 50, which you can see by these white missing data points now in this data set. Since I am just averaging the data, I'm not even going to worry about replacing those. Each of those points is probably about a second, and I'm planning on averaging, generally you're planning on averaging tidal ADCP data in 5 or 10 minute intervals. And if you're sampling at 1 Hertz, then a few missing points out of 300 or 600 is not going to do a lot statistically. I mentioned before that this is vector velocity, and so we do eventually want the data most likely in east, north, up coordinates. You can set them to streamwise coordinates where your main vector is aligned with the main flow through the channel, and then your other 2 directions are your 2 perpendicular directions, usually cross stream and vertical. To get to east, north, up, the instrument does have a compass. It is a magnetic compass, so you should Google what your magnetic declination is at the spot you're recording, and there's a function to set that properly. Once you have that set, it's fairly easy to use this rotate to function to specify a coordinate system and then rotate it there. I do also show how to, if you want to go into the streamwise coordinate frame, you need to calculate the principal heading. So the principal heading is essentially the degree from north that your main flow stream is moving in. I show how to do that here. Finally, to average the data, there's a couple steps here. Instead of just 1 step, we set up a class, a binner class, that and the 2 main points we need to give it are the number of data points to window. Essentially, you're taking individual windows every, in this case, 300 seconds, and then we're grouping them together with the bin average function. And so what that bin average function will do, as I said, is we'll window and average each data point in the window. This will massively reduce the size of your data and also massively reduce the noise and uncertainty in the data itself. The new data set that gets returned here will look a lot like the same, essentially look identical to the old data set, except with a shortened time variable. And in the interest of time, I'll pass through that. Most ADCP analysis you're doing might stop there if you only care about ADCP velocity. The last thing you might want to do is calculate your speed and direction. This can be a better way of visualizing it. So just to jump through some plots, so it looks like I do make some matplotlib plots. I calculate the speed here with the blue line denoting the water surface, and then I calculate the direction. In this case, I think it's a south flowing ebb tide, clockwise from north. No, ebb is flowing north here. So 0 degrees means towards in terms of water current. Finally, you can save. You can save your data in .cdf files. You can use them using these functions. And then finally, turbulence intensity. That is essentially what you're getting with turbulence intensity is the percent from the mean flow that you will see fluctuations over. So once you create this average data set, you can run this, what we call a shortcut. This is an X-ray specific what's the word I'm looking for? Jargon, annotation, function. That's the word I'm looking for. And then the shorthand I is what what Dolphin is using for intensity. And you can add, you can calculate that, you can plot it, and you can see how your turbulence intensity varies over the course of your profile. I think I'm going to end it there. If you're interested in the more detailed specifics of velocity and frequency domain analysis, you can cruise through the rest of this notebook. But I will go ahead and stop there. And do we want questions now, or shall we move on to the next? What time we at? 11:47. Wow, I took a lot of time. Okay.
No worries. Yeah, if anyone has questions on this example, go ahead.
I'd ask you, James, what is the challenge in reading ADCP files? Why is it so hard?
Great question. Each manufacturer has a special way, has their own proprietary way of storing these large data files. Obviously, the best way to do that, the most compact way to do that, is to store it as binary. And so when you're storing more complicated, this is the same. It's the same way for a lot of instruments out there, like hydrophones. When you're storing a lot of information, you need to do it compactly and in a way that can be easily read by you if you're making the file after the fact. So essentially what these files are is that the manufacturers are storing a large configuration block of data in the file, and then each of those pings is a separate block of information. And so what Dolphin is doing is reading through this configuration and data blocks based off integrator guides that the manufacturers share. The big plus about using Dolphin is that you don't have to use the manufacturer's tools, which are usually good for generating things in MATLAB and don't give you the metadata. So if you're new to these instruments, it's pretty confusing to get started and get going with. Nortec and RDI do have paid software that will read the data and do all of this processing for you. I forget how much they charge for them, but if you don't have a lot of time and want to get it done fast, their tools work as well. But the pro with Dolphin is it gives the power to the people. Wanted there. Mara, give a question.
Yeah, thank you so much for the presentation. I've worked with current data for a long time, so I do know what kind of mega undertaking this was. I'm curious for if you don't have a pressure sensor on your ADCP, is it easy to read in pressure from nearby data like a RBR or something along those lines?
Yeah, you'd have to write your own Python code to do that, but you can just store it as that. You can just add a variable called pressure to the X-ray data set and save it in there. You'll probably have to interpolate the time or match up the timestamps or sync up the timestamps to do that. But yeah, you can definitely do that.
Okay, great. Thanks.
Dolphin really just cares about the variable name and then its dimension sizes. If no other questions, I'll send it off to Andrew. He can explain MATLAB, the MATLAB side of MHKiT for us.
Cool. Thank you, James. Can everybody see my screen?
Yep.
Awesome. Okay, so first here, I'm going to start just looking at the MHKiT documentation. This project has incredibly good documentation, and I'm not just tooting my own horn here. I use this all the time. So if you're curious or you want to look more at this, there's stuff for the API documentation specifically, and then how to install on Python and MATLAB. I'm going to jump into the MATLAB installation really quick. It's a little complex just because the way we interface with Python requires a little bit of extra work. So if you're curious here, this is outside the scope of this install, but these are all the steps you need to actually install MHKiT MATLAB. I'll quickly roll through how I would practically do this, and if somebody specifically asked me, this is how I would roll through this here. So we're on GitHub. We're in the MHKiT software project and then the MHKiT MATLAB repository. And where you want to go is in this releases link here. And then I'm going to scroll to the very, very bottom. And the two things you need is the MHKiT examples and the MHKiT MLTBX file. The MHKiT examples are going to contain all of the data and code for the examples. So I'm going to go ahead and save that just to this folder on my computer. And then I'm going to save the toolbox also, same place. And then all I need to do to get this into MATLAB is to open those two files. And so it basically looks like this, and I'm just going to double click I've done this a bunch of times just to make sure this works. So right here, I double click this, and then this is gonna go through the installation step. It's really quick. And then you're gonna have the MHKiT toolbox installed. And practically what this is doing is just putting files on your computer. So it's literally putting stuff in this directory right here. And then to run this, all you need to do is, there's a command we have in the documentation where we run this circular function. And I'm just gonna hit enter, and I get no errors, which is good. So to kind of start this discussion here, the first piece of this is kind of like, what do I do, or what can I do in MATLAB? And one of the first things you can leverage is the help command. And so if you know what functions exist, and I can show you what functions exist in a second, you can just type the help command and you can get the doc string from the function, or you can just open the function and take a look at the code. And so this is going to tell you what the parameters are, what the inputs are, what the expected units are. This piece is pretty important. We don't do any unit checking or error checking in this sense, and it'd be garbage in, garbage out for this specific situation. So highly encourage everybody to leverage the documentation where it exists. And so right here for MHKiT MATLAB, it's going to be in the API documentation. And then you click right here on MHKiT MATLAB API, and you can see everything that exists here. So the next thing I'm going to show you guys is we're going to run through. One thing I skipped just really quick. You need the specific version of Python with a specific version of MATLAB. This is in the documentation also, and on GitHub, there's issues. Please submit an issue if there's any problems with the installation. There's an incredible number of variations of how this project could be installed, and I try to capture all of them, or we try to capture all of them, but there are definitely some edge cases, so please let us know. I think sometimes people hesitate to put issues, but please do, and we can fix everything. We're all pretty good at fixing stuff, but we don't necessarily have the expertise to test in all these different systems. And so I went through the quick install here. And then the first example I'm going to go through is wave energy converter power performance. This is 62600-100 and 62600-101. And to do this assessment, we need a power measurement, and we need a surface elevation of time series, or a time series of power spectral density. And in MHKiT, we're going to compute power spectral density, the significant wave height, energy period, omnidirectional wave flux, and then the energy flux matrix and the power matrix. And what's really cool is in MHKiT, each of these is a really simple function. And so we've kind of taken the standards and made the API really simple and really standardized, so that if you were doing this computation, you could do this with a model of data, you could do this with real world data, and you get these standardized outputs based on the IEC standards. And so in MATLAB, I'm going to go ahead, I'm in this examples folder, and then you can see here's all the examples that exist. And you're more than welcome to take a look at any of these. These are all complete, and these all have different goals that they're trying to achieve. So I'm going to go ahead and open up the wave example here. And first thing I'm going to do, good MATLAB practice, is clear everything. And so as we walk through this, I'm certainly not the expert in wave energy specifically. And so it's great as a data scientist that I can leverage some of the embedded knowledge in this project to do this type of analysis, and to help others on our team leverage some of the other tools that are available in the standards and within MHKiT. And usually, to be honest with you, what I like to try to do when I first look at these is scroll all the way to the end and see what the goal is. And so for this specific example, the goal is generating a mean capture length matrix. And if you're familiar with the standard, you'll know that this got changed to capture width matrix. So we need to update all of our documentation here. So looking through, this is really what we're trying to achieve here. And then if you also notice, if you're familiar with wave energy, this number doesn't really make any sense. We don't have real world data for this specific example. We'd love it if there was some, and maybe somebody on this call has an idea of data we could use for this example. That'd be great. And so starting at the top, what we're going to do is load in some data from the NDBC. So I'm going to go ahead and just, so if you're in these, oh, I skipped one thing here. So in MATLAB, there's something called a live script, and then there's just straight up MATLAB code. This is running as a live script. We also provide just the .m files. If you want to see just the code, this will run exactly the same way. The live script is a little easier to kind of work with and use, and it'll put the plots directly here rather than generating a bunch of extra figure windows. So I'm going to go ahead and run this. What this is doing here is we've cached a little bit of NDBC data, and we're going to go through and download it, parse it, look, kind of explore some of the data, and then compute the quantities of interest we need to do the -100 power performance assessment. And in MATLAB, we have all the variables here, and so we can kind of do this exploration. MATLAB users typically use data in a bunch of different ways, and I think it's actually a really interesting platform for looking at data from kind of like a hands-on perspective. So I can click through some of these things over here, and if I want to just look at HM0, I can quickly go here, plot it, just kind of do like a sanity check on the data as we're kind of working through. So I'd highly encourage, if you're working on this, leverage all of the MATLAB tooling that exists to explore this data as you're going through. And then the other thing that's cool here is if I have any questions like, oh, what's the input to this function? Same thing, I can just open this function and see the documentation here. So a ton of work has gone into in MHKiT to having really good documentation with really good idea of what the units are. So back to the example. So we're going to first take all this data. It's in spectra, power spectral density, or power spectral density computed values, and then frequency here. And we're going to use that data to calculate the energy period time series. You'll notice here, I don't need to say, hey, iterate through all these spectra and calculate the energy period for each one. The APIs basically pass in data in this expected format, and we can calculate the arrays of data for you. So we're visualizing energy period here. This would be wise, especially for me as a data scientist, to leverage the other folks on my team to make sure that these values make sense. And so same thing here. This is going to be from real world data. There's no guarantee that this is perfect. So this needs to go through some level of validation. We typically trust the NDBC and CDIP that they're producing good data, but I would always recommend trust but verify. And so let's see, so we've got energy period. We're also going to calculate significant wave height. The typical nomenclature is HM0. Same thing here. If you wanted to look at the doc string, you would just click here and go open. And then so we have HM0 TE. We're also going to need the depth to compute the energy flux. This is can be found typically in the metadata of the instrument, or here we're just setting it directly. Inside of the standard, this changes the way you calculate energy flux. This has to do with how the waves reflect against the bathymetry. So we just want to make sure it's actually not going to let you calculate this if you don't have this set as a value. And then right here, we're going to generate some power data. This is obviously not representative of the real world. This is just for this example. If you were using a model or using some real world data, this is where you'd pass it in. The units would be in watts. And then as we start to get into the standardized calculations, same thing here, simple API. So capture length is going to take an input of a power time series and omnidirectional wave power time series and calculate the capture length. Again, here this should be capture width. This is something we're actively working on. And then the IC standard calls for calculating the mean, the standard deviation, the count, JPD, basically the min and the max of the capture length matrix. So we have all the function arguments available to calculate these specific matrices. And then we're just going to do some visualization here just as another sanity check of the data. This is transposed, so typically you would see it here if you see in the visualization below. But again, here just following that practice of trying to take a look at the data as we're going through. Per -100 edition 1, we're going to calculate the power matrices. And for that, it's another simple API. Once we have the data, we pass in the significant wave height, energy period, omnidirectional wave power, and then we specify that we're calculating the mean, and then we give it the bins of data, and same thing here, we get a matrix output. There's a couple of details in the standard where there's different ways to do this calculation. We note it here that there's some non-standardized ways to do this also, but we try to encourage users to use the standard methods where applicable. Right here is pretty awesome. This is getting kind of to the results of this, and so we can take the L and J arrays and calculate mean annual energy production, and then also calculate it from the matrix here. This is per the standard 62600-101. So this is a pretty cool thing. We can just kind of really quickly understand this. This is going to take all of the data for the entire year and give us a number, give us an idea of, or sorry, not an idea, a calculation of the energy output over the year. And then at the end, we're going to try to generate all the visualizations per 62600-100. One of them is the capture length matrix. And so we've got all of our bins noted here, and then our units. And this would be one of the outputs. We would continue on to actually calculate the standard deviation of the capture length matrix, the mean and the max, and then those would go in our final reports. So that's how you would run through the -100 standard in MHKiT. And then building on that, if you wanted to do something a little bit bigger, or you had a different question, we can leverage some modeled data. And in MHKiT, we have functions to download data from the WPTO hindcast data set. And one interesting question here is kind of like, well, we have real world data, we have NDBC and CDIP data. Why would you want to use hindcast data? And one of the answers is this data for some of the locations is complete. And so you could look at a whole entire data set from 1979 to 2020 to try to get an idea of what a model is predicting. And an interesting question we typically get for this project is, what is a hindcast? It's basically taking the known conditions and computing what the wave height was at a location where there wasn't a measurement. So it's the opposite of a forecast, but it's the same idea where it's modeled data. And so in MHKiT, we're leveraging data that's available at all of these locations. And the API is basically, we put in a quantity of interest, a year, and a latitude, longitude, and we can get out these quantities of interest at a specific point, and we can do time series visualizations, calculate energy flux matrices, joint probability distributions, and do the same extreme sea state modeling there. So this is pretty powerful. If you're able to leverage the hindcast data set, there is multiple gigabytes of data, and then I'll show you guys really quick. These data sets are huge. So if you wanted to look, this is actually a pretty small one. If you wanted to look at the West Coast wave data set, to do this work, you could download, let's see, what is this? 89 times 32. So it's like probably 5 or 6 terabytes of data. Or at NRO, we were able to work on this on the HPC. But if you're a typical user, it's really convenient to be able to say, hey, I want to know what's going on at this specific lat long. Pac wave south, and do some calculations on that. So I'm going to go ahead and run this. This is unfortunately a little bit slower than really quick access. And basically what's going on behind the scenes is we are leveraging this original data and then slicing the data at a single point. So I'm going to go ahead and run this. In MHKiT, we try to cache the data where it's possible. And so you'll see as I run this, it's going to read the data from a cache. And so as I roll through this, I think I've ran this before, maybe we're doing very similar calculations as we've done before. So we're going to get significant wave height, we're going to get energy period, peak period, omnidirectional wave power, and time. And then we can leverage that to do the same kind of analysis that Adam showed you with the NDBC data. So trying to make this available and easy for users to use, and then leverage this for multiple types of analysis. And our team is using this really frequently, and I've been using this to try to make joint probability distributions at multiple locations for a project we're looking at. And it's really awesome to be able to just leverage all the kit that's available, or all the code that's available in MHKiT to do this analysis in MATLAB. So. And let's see, so really similar data to the NDBC, and we can do all the same types of computations. And so joint probability distributions, we can leverage some of the box plotting. We can do some of this contour, extreme wave condition modeling. And there's some extra parameters here for we're requesting data from the hindcast with 2 points. And then we can do that comparison. And then there's a high resolution data set that's also available for 1 hour data. The typical hindcast data set is 3 hour time spans. So there's a bunch of different things you could do with this, but in general, NDBC CDIP data is going to be at specific points, and it's not going to be a complete data set for multiple years. And then the hindcast is going to be multiple years, complete data sets, but it's from a model. And so depending on your use case, you're going to want to try to pick the correct data set. And then one other piece here, just like a heads up, is this example is almost identical in Python and MATLAB. And so if you're looking at a bunch of these examples and you're looking at this code, we're trying to be really similar, if not identical, for different programming languages with the same API. So if you have developers working in Python, the API can be really similar to developers working in MATLAB. And with that, that concludes the MHKiT MATLAB portion of this, and I'm going to hand it over, I think, to Adam to wrap this up.
Thanks, Andrew. So I think, Dominic, we're done with our demos and on to questions now.
Great. So if anyone else has any questions about any part of the demonstration, feel free to jump on and ask away. Seems like we already have two. Maybe Jonathan, you go first.
Yeah, just a quick question. Between the MATLAB and the Python versions of MHKiT, are there any unique capabilities offered in one but not the other, or are they pretty synced up?
Want to take that, Andrew? I think you're
Sure.
most up to date.
They are relatively close. For our team, there's it's much more, sorry way to say this. We heavily leverage Python first, and then we kind of come behind and put it in MATLAB. So I would say maybe 80% of the code in MATLAB is up to date, maybe 90%, and then we're trying to kind of catch up. And so for us, our actual goal this year is to try to get to parity where MATLAB and Python have really similar APIs and really similar functionality. But at this point in time, the only thing really missing is the acoustics module, which is pretty new. So everything else should be really similar.
Great. Andy, did you have a question?
I have a question. Is there another Andy you're asking about?
No, that's you. That's you.
Oh, I'm listed as Andy, right? Yeah, okay. I have a question for Andrew Sims. You mentioned that your capture width length example is lacking real data. I think I can supply that for you for our small system. It should make sense. We have probably quite a bit of years worth of data or so that would have co-located wave measurement along with the power production of the buoy. So that's something we've talked about actually the two groups before, but we've never really executed on. So I think that would be something to do. And what you can do is we're going to give in 2 weeks the software demo days presentation on our project. So you can come to that, check it out, and then after that you'll know more about the system, and then we can talk about how to move the data.
That's awesome. I was hoping you would chime in at that point.
What's that?
I was hoping you would chime in at that point because I was thinking you had some data for us, which is great. It's great for us to use the tools and then cross collaborate if there's things we can be helping you with.
Yeah, no, you're tackling a hard problem here. I mean, Michael Anderson is on the call here from Embari that we're talking about this morning. It's like all this data is getting collected, and it's like, well, what do we do with it now? So yeah, so we can do that, and I think a lot of the data I'm talking about was published, the results of a comparison between the field data and WEXIM model and the R simulator. So a lot of the data I'm talking about is kind of already in the public domain, at least in a reduced way, and we can talk about how much is publicized to your thing. So yeah.
Awesome. Yeah, well, we should work with the team and try to figure out how we kind of move forwards with that. But that sounds great to me.
Cool. All right. Nice job.
Thank you.
Any other questions? If there aren't any other questions, I guess I have one. What other projects are you guys using MHKiT on?
I could start. Right now, well, I sit on both the MHKiT and WEXIM teams, and so working to connect them together better and make them, for example, make some examples about processing WEXIM outputs that are run on resource characterization from MHKiT. I'm also using MHKiT for a variety of team rewards myself.
Makes sense. I figured Teamer would be in there somewhere. So yeah, if there's no other questions, leave it just a second.
Just one other line to put out there, because since Adam and Jonathan are here, there has been an effort going on behind the scenes to get MHKiT and Primer to kind of like work together, so that some of those IO functions that the MHKiT project has, so that it can also use some of all the data that we have in Primer. We haven't gotten to it yet, but maybe in the next FY or so we can try to prioritize that.
Yeah, sounds interesting. Hopefully useful now. So if there's no other questions, I'll share my screen and we can wrap up. I know we're getting close to time on the demonstration. So as we were just talking about actually with Andy, so the next demonstration is MBARI WEC. That'll be on June 4th at 12 p.m. Mountain Time. So be sure to tune in for that. This demonstration was using CoCalc, the next one will not. But the next one, I got some links for us. This is just some information about installation and preparation for the next demonstration. So I'll put these links in the chat, but you can go to the GitHub of MBARI WEC and follow the installation instructions. And if you find any issues that you can't resolve, reach out to Andy or Michael.
Yeah, can I chime in on that?
Absolutely.
Yeah, so we're going to do this demo, in a way that this is a little bit of a, you're going to have a Linux computer and do an install. So for people with that background, it's going to be, I think, straightforward to do what's on this screen, but maybe not everybody's going to reach to that real easily. So we're going to do our demo in a way that it could be hopefully useful if you haven't done it. That is, install the software. But if you do install the software, that would be great from our point of view, and we are here to help. So if you have any trouble in the next 2 weeks, there's my email and Michael's. Just make sure you email us. You can also we monitor the GitHub issues there. There's a link to that. That's a great way to do it, is that other people can see the discussion. But if you just get really stuck, just call us. Yeah. Okay, thanks.
Yeah, thank you. So that wraps it up. Megan, what's up?
Yeah. So just kind of piggybacking on what Andy said, I'm going to be sending out an email with all of these links right after this, so you'll have that handy via email as well if you don't catch them in the chat.
Great. So yeah, I'll briefly open the floor to any other questions that might be applicable to the demonstration days meeting series or anything else. And other than that, that's it. Thank you everyone for attending.